Thank you very much, and thank you all for sticking around. I'm Dumitru, I'm an LP fellow here at Oxford, and today I'd like to talk to you about something deceptively simple. What happens when electrons slow down dramatically? And the title of my talk is The Physics of Flat Electrons, and as you will see, this idea sits at the crossroads of band theory, topology, and strong correlations, and it leads us to some of the most exotic phases of quantum matter known today. Before I start, however, let me make a disclaimer. I understand that the title is a bit of a clickbait. I'm not a flat electronist. We haven't discovered the new fundamental particle. Flat electrons aren't exotic entities beyond the standard model. They're just the plain old electrons, same charge, same spin. But they behave in very unusual ways inside certain materials. Now this XKCD comic here makes a playful jab at the scientific hierarchy. Physicists at the top, of course, but it misses something crucial. The idea that biology is just applied chemistry and so on breaks down once you realize that the key player is emergent behavior. As Phil Anderson, shown here, famously put it, more is different. When electrons are confined to nearly flat bands, their interactions dominate and they give rise to collective phenomena that are completely invisible at the microscopic one-electron level. So yes, they're just electrons, but in the right environment, they become the seeds of superconductivity, magnetism, charge fractionalizations, things that no individual electron can do on its own. So, to understand what it means for electrons to be flat, we first need to talk about what it means for them to be dispersive. So before diving into all the exotic physics, I'll start with a quick refresher of band theory, how electrons move in a crystal, how energy bands emerge, and what we mean by dispersion. This will set the stage for understanding what it means to suppress that motion and how that can fundamentally reshape the many-body landscape. So let's start from the free electron model. If we place an electron in a perfectly uniform background, as shown here on the left, there's no potential at all, its dispersion is just a plain, simple parabola, right? We know that the energy is h squared k squared over 2m, right? P squared over 2m. That's what we see on the left. Now, when we move to a crystalline solid, we break the continuous translation symmetry to discrete translation symmetry, right? In a crystal, the momentum is only defined up to a reciprocal lattice vector. In this case, it's 2 pi over a, where a is the lattice constant. This essentially folds back the dispersion of the free electron inside the so-called Brillouin zone. But of course, the actual crystal does have a potential with a discrete periodicity. And after we add the periodic potential, as shown on the right-hand side, we see gaps opening and bands, electronic bands forming. So what we get at the end is a band structure. Electrons still propagate, but now they do so with a modified dispersion that reflects the periodic environment. This is the basis of the nearly free electron model. Still delocalized, still momentum eigenstates, but dressed by the periodicity of the lattice. Now let's switch perspective, and instead of thinking about free particles perturbed by a lattice, we can start from tightly bound electrons, say in atomic orbitals. Here I'm showing S, P, and D orbital levels. They're localized and discrete, right? I'm showing them here on the left-hand side. The first step is to imagine copying these atomic orbitals across the lattice. Now we have one orbital per unit cell, repeated periodically. That gives us a flat band structure, no hopping, no dispersion. We've simply multiplied all these energy levels and added a momentum to them. Then when we allow these orbitals to hybridize, which means we allow the electrons to hop between them, each level broadens into a band with a bandwidth controlled by the hopping amplitude. This is the so-called tight binding model. It's the polar opposite of the nearly free electron case. Instead of starting from momentum eigenstates, we now start from real space orbitals and let them communicate. In the end, both routes lead us to the same concept of bands, which are just continuous energy levels, right, that the electrons occupy, which are labeled by crystalline momentum. Now, let's talk about what happens when we account for electron-electron interactions. Electrons, of course, they repel one another. They carry the same charge. So we can't just take those bands and fill them with electrons as if they were non-interacting particles. Real electrons collide and they scatter and they exchange energy and momentum. But remarkably, for many metals at low enough temperature, the system behaves as if it were non-interacting. And this is the magic of Landau's Fermi liquid theory, one of the great triumphs of condensed matter physics. What Landau postulated, and later Abrikosov proved, is that even when electron-electron interactions are present, the system can still be described in terms of long-lived quasi-particles. These are not bare electrons anymore. They're dressed by the interaction with the rest of the electronic sea, and they require modified parameters, such as modified mass and lifetime. When I was an undergrad in Cambridge, someone explained to me the concept of quasi-particles using this exact same diagram, saying the real particle is a horse and the quasi-particle is a quasi-horse, which at the time seemed just as helpful as it sounds. But to their credit, it is a vivid way to say that the thing that you care about, the thing that you see, isn't the bare object, the bare electron. It's the bare object plus a cloud of particle-Hall excitation. Microscopically, this whole theory, this whole Landau Fermi liquid theory, can be understood using many-body perturbation theory. But critically, that only works when the electrons are dispersive enough such that the interactions stay in check. Once that fails, the Fermi liquid theory breaks down. And that's a very good thing, because otherwise condensed matter physics would be a very boring subject. So now let's take this logic and flip it on its head. What happens when we're trying to partially fill a band that is flat? In that case, the kinetic energy, the dispersion, becomes negligible. That means that this bandwidth, W, is much, much smaller than the interaction scale. Sometimes it's even much smaller than the energy gap. This is the regime where Landau's theory completely breaks down. In a dispersive band, you could treat the interactions as a small perturbation on top of a dispersive band, but in a flat band, there's no free motion. There's nothing to perturb against. Your unperturbed Hamiltonian is zero, right? So in fact, the situation here is reversed, right? Interactions dominate and kinetic energy becomes a small perturbation if it even exists at all. So we can't start from a non-interacting solution and perturb our way out. We're forced to tackle the many-body problem full on. Now, these flat bands may feel like a hot topic now, but have actually played quite an important role in condensed matter for decades. You could loosely trace some of these ideas back to heavy fermion materials in the 70s. These aren't flat band systems in the strict sense, but they're often grouped in the same family because they exhibit narrow bands as strong electron correlation. The first truly flat bands in the sense of the term of today appeared when Landau levels in the quantum Hall effect, both in the integer and fractional one, were discovered. These discoveries were nothing short of revolutionary because they each earned a Nobel Prize and showed that interaction-driven physics in flat bands can lead to entirely new quantum phases. The modern flat band renaissance came with twisted bilayer graphene in 2018. So if you have two layers of graphene, many of you might remember this from last term's morning of theoretical physics. If you have two layers of graphene and you rotate them at an angle which is close to the magic angle, then you can actually show that flat bands where interactions dominate emerge, and you have superconductivity, correlated insulators, and more. Today, this platform is evolving. We now have fractional Chern insulators, which basically exhibit the fractional quantum Hall effect without an applied magnetic field. But there's a question which hasn't been answered until recently. Can we get these flat bands in conventional crystal, ordinary crystals. No twisting, no stacking, no moire magic, no magnetic field. This is what I'm going to try to answer in my talk. So to really motivate why flat bands are exciting, let's take a closer look at a system that recently reignited the field, right? This is twisted bilayer graphene. So you take two sheets of graphene, you rotate them relative to one another at an angle of 1.1 degrees, and the resulting moire patterns flattens the bands near charge neutrality. What you're seeing here on the left are actually 8 nearly flat degenerate flat bands, right? 2 for each valley, 2 for each spin, and 2 for each layer. They're clustered around the zero energy. Now here's the key. These bands are gapless in the non-interacting model. But if you try experimentally, if you try to fill these bands and you fill an integer number of them, you see that the interaction effects kick in and the system develops and gaps open. These are so-called correlated insulator states labeled here in this schematic diagram on the upper right. Between these fillings, the system can enter a superconducting phase. These are the blue SC domes, which emerge entirely from interaction, since there's no phonon glue here. And the richness doesn't stop here, actually. Twisted bilayer graphene has shown signatures of something called the Pomeranchuk effect, which means that with increasing temperature, you actually cause the system to order. This is somewhat analogous to the Pomeranchuk effect in liquid helium, where actually heating the system makes liquid helium freeze. So you have only one material, and the only knob is the carrier density. And we see correlated insulators, superconductors, strange metals, quantum dot behavior, all stemming from these flat bands. Now, to really understand the interplay between interactions and band structure, let's start with the Hubbard model. The Hubbard model is arguably the simplest model of interacting electrons on a lattice. We have fermionic creation and annihilation operators that I'm denoting here with C and C dagger, right? And the number operator n. The Hamiltonian has two main terms. The first one is a nearest neighbor hopping. So this one will take one electron at site r prime and hop it onto the site r. And we have an interacting term which takes the form of on-site repulsion and penalizes double occupancy of a site. There's also a chemical potential term which controls the filling of the system. This model actually lets us smoothly tune between two extremes. When t is 1 or t is much larger than u is 0, we're in the non-interacting limit. As we tune just a little bit of on-site repulsion, we enter into a Fermi liquid regime where perturbation theory applies. So all is well. When we take t is equal to 0, then it turns out that we're in the exact flat band regime. There's no dispersion, and interactions fully dominate. And this is the punchline, just having a flat band isn't enough to guarantee interesting physics. As we will see now, both limits, both the non-interacting and the exact flat band limit, are exactly solvable, and neither captures the richness that we saw in twisted bilayer graphene. So let's begin with a very simple exercise and look at the non-interacting end of the spectrum. Right, we set the on-site repulsion to 0. In this case, the Hubbard model reduces to a textbook tight binding model that you might remember from undergrad. Right, electrons hop between lattice sites with a certain amplitude t, and you can diagonalize this Hamiltonian in momentum space. The ground state shown here is just a filled Fermi C, right? You simply take the electrons and occupy the lowest available momentum states up to the Fermi level. It's completely solvable and completely benign. Now, if you add interactions, but they're still weak, yet non-zero, we're in familiar theory. We can apply many-body perturbation theory and describe the system in terms of Landau quasi-particles with renormalized parameters. This is the Fermi liquid regime that we talked about earlier. But now, as we move towards stronger interactions, this description begins to fail. The system starts to develop correlations that can't really be captured by perturbation theory. So now let's go into the opposite extreme, the flat band limit, and see what's happening there. On the opposite end of the axis, we have the flat band limit. We set the nearest neighbor hopping to 0. In this case, hopping is completely switched off. The system breaks up into isolated lattice sites, and there's no communication between them. So the full many-body problem really reduces to solving a single-site Hamiltonian. Each site has 4 possible states. I can have an empty state, a spin-up state, spin-out state, or both electrons, right? Doubly occupied state. The energy levels are trivial to compute, and really there's no emergent behavior. It's just a 4-level system. And this is really the key message. A flat band on its own isn't enough. Even if you have strong interaction, if the system has no structure, and I'll explain exactly what that structure means, it's basically topology, there's no connectivity, right? You don't get anything interesting. So if you want to explain the richness of a system like twisted bilayer graphene, we need something more. And the missing ingredient is actually non-trivial band topology. And this leads me to the first proper part of my talk, right? We've seen that neither strong interactions nor flat bands alone are enough to explain the richness we observe in a system like twisted bilayer graphene. So the structure that is missing is a way to characterize how bands are built and connected beyond just their energy, right? This is exactly where topological quantum chemistry comes in. It provides a systematic way to understand band structures in terms of symmetries and orbital content, telling us exactly what a band is made of and what it's allowed to do, right? In this next section, I'll introduce some of the key ideas of TQC, topological quantum chemistry, and show how they help us navigate the space of possible flat bands, especially those that are topological. Now, depending on your background, you might look at a material like graphene from 2 very different angles. If you think like a chemist, you will think about graphene in real space. You have orbitals, you have bonds, you have hybridization, but if you're a physicist, you're drawn to these spaghetti-like plots, which are in reciprocal space, right? So you introduce concepts such as Brillouin zones, dispersions, band crossing, and so on. But there seems to be some kind of a conceptual gap, right? On the left, we have localized atomic orbitals, right, which feel very intuitive. But on the right, we have a band structure which is completely delocalized. It's a momentum space object. Now, if we want to understand topology, this relationship between the real space and the reciprocal space is absolutely crucial. Topology, in a strict sense, is a global property of bands in momentum space. Things like Chern numbers, which require that you integrate, right, across the entire Brillouin zone. But these topological features, and this is the key idea really, must have a fingerprint in real space, because electrons really live in orbitals. So what we need is a formalism that connects the real space orbital content to momentum space topology. And this is exactly what topological quantum chemistry does. So far, we've been talking about band structures, right, in terms of eigenvalues of certain Hamiltonians, right? But to really get the connection between real space orbitals, symmetry, and topology, it will be actually helpful to mod out the energetics, right? In other words, let's ask the following question. Can we talk about band structure without ever writing down a Hamiltonian? And the answer is yes, of course. And the way you do that is you lean on symmetry, because crystalline materials are defined by a symmetry group, right? Something called a space group, which encodes all the allowed symmetry operation, right? You have translation, rotations, reflection, and such symmetry operation, right? Given a space group, you need to add only 2 more ingredients, right, to fully characterize a crystal. The position of atoms within unit cell, right, and the orbitals that each atom contributes to the band structure, right? With just these 3 ingredients, space group, atomic position, and orbital character, you can ask, what are the possible types of band structures that are allowed by symmetry, right? What are the possible band structures that I can get in a real crystal? And this is the central question of topological quantum chemistry. And the answer comes in the form of something called elementary band representations. These are symmetry-based building blocks of all electronic band structures. So let's build some intuitive picture, right? You fix the space group, right, which are the symmetries of a crystal, but you're still not done, because there's a lot of freedom on how you place atoms within unit cell, right? And that freedom matters. Take this example. All these 3 structures here share the same Bravais lattice. They're built on a triangular lattice, right? But depending on where you put the atoms, you can end up with a triangular lattice, a honeycomb lattice, or a Kagome lattice, each with different numbers of sites or occupied sites per unit cell and different symmetry properties. The key is that in all of these cases, the atoms really are placed in ways that respect the space group symmetry of the lattice. But the specific arrangement, right, what we call the Wyckoff position, will determine how the orbitals transform under the symmetry, and therefore how the bands connect in momentum space. So any theory of elementary band representations has to take this into account. You don't just need the lattice and the orbitals, you need to know where these orbitals sit. Once you fixed the lattice, once you fix the atomic position, you still have another important detail, right? What orbitals you put. Because different orbitals transform differently under the symmetry operation. So they generate different band structures, right? In both cases shown here, I've chosen my occupied lattice sites to form a honeycomb lattice, right? On the left, we have s orbitals, right? And this should give you something graphene-like, right? With Dirac cones and symmetry and forced crossings. However, on the right hand, we place px and py orbitals instead. They have very different symmetry properties, right? They point in plane, they will hybridize differently, and the resulting bands will behave very differently. So full theory of band representation has to consider not just where the orbitals sit, but also what kind of orbitals you have, right? The symmetry of the lattice combined with the symmetry of the orbitals determine the representation content of the band. And this is how topological quantum chemistry builds all the bands without Hamiltonian. So not with a Hamiltonian, but from symmetry ingredients, right? So now, once I've introduced all these ingredients, it's time to tell you what the main idea of topological quantum chemistry is. We want to classify all possible band structures that could arise from electrons sitting in real space orbitals, right, that obey crystalline symmetries. And we want to do that without ever invoking a Hamiltonian. So the way we do that is we think of bands as being representations of space group, right? And these representations are these elementary band representations. To cut a long story short, what people have done, and only recently in 2017, they've taken all the possible space groups, all the possible ways of arranging orbitals in them, and they've carefully tabulated every single band that can arise in such system, right? Every single band that can arise from localized real space orbitals, right? And then they said, well, we know all the bands that have a localized real space description. We also know all the possible bands, right? Because we know how bands should connect in momentum space, right? and they reach the following conclusion. All sets of bands that are not induced from symmetric and localized orbitals are topologically non-trivial by design. So, of course, you can read a lot about topology, right? You have rather complicated topics such as Chern numbers, right? Invariance in momentum space. But this gives you a very simple intuitive explanation. So let me visualize that. This diagram shows the landscape of all possible band structures that are allowed by symmetry. That is, all bands that satisfy the connection, the compatibility relations in momentum space. Within this full space, we have a distinguished small subset, these elementary band representation. These are band structures that arise from symmetric localized orbitals in real space. In other words, atomic limits. And here's the punchline. Not all symmetry allowed bands come from a localized real space description. By definition, such bands are topologically non-trivial, right? And this diagram captures the logic of topological quantum chemistry. Let's have a very simple example, right? Suppose you have a group of bands, right? And you want to ask, are they atomic or are they topological, right? The idea of topological quantum chemistry is to try to express these bands of interest, right, which are the filled bands in all these cases, as linear combinations of elementary band representation, right? On the left, you have a band structure that's just a single elementary band representation. That's atomic. There's no surprise there, right? It's induced from localized symmetric orbitals, and it has an atomic limit. In the middle, you have a case where the bands decompose into a fraction, like a rational non-integer combination of elementary band representation, right? By definition, in such a case, your bands are topological. They do not admit a localized real space description, right? And of course, you can have other situations where the bands are actually an integer linear combination, but one of the coefficients is negative. I will not go into the details, but those are also topologically non-trivial. So the main takeaway of that section was that a band is topological if it doesn't have an exponentially localized real space description, right? Armed with this information, we're finally in a position to talk about the central question that I posed at the start of the talk. Can we realize flat bands, ideally with non-trivial topology, in conventional crystalline materials? So until now, we've seen that flat bands really emerged in either engineered platforms, right, or with strong magnetic fields. So we want to replicate the same type of physics in ordinary, honest crystals, right? With materials with no fine-tuning, no moire, no external magnetic field, none of that. Okay, so why do we want topological flat bands, right? I gave you this example with a simple Hubbard model. But why do we really need the topological aspects? This is because not all flat bands are created equal. This is where the topology comes into play. If your flat band is trivial, as it happens here on the left-hand side, right? If you Fourier transform the flat band, you get exponentially localized real space orbitals. If you try to write down an interacting theory for that flat band, what you end up is essentially a local term that looks like the Hubbard interaction term we saw earlier. So there's nothing special about this, right? You can decouple the sides, and then you can solve each side separately, and there's simply nothing special about these bands. In contrast, if you have a topological flat band, then you really cannot build this localized real space description. Either you can't have the orbitals be symmetric, or in most cases, you can't have them be exponentially localized. So when you build an interacting theory for orbitals such as these for a topological flat band, you find that the interacting Hamiltonian is highly non-local. Even though there's no kinetic energy, the projected interaction is non-local, and the physics is far richer. And this is exactly why topology matters. As I show in the schematic here in the bottom right, the most exotic phases in condensed matter tend to emerge precisely where this non-trivial band topology meets strong correlation. And this is really the target zone, the upper right quadrant here of this phase diagram, where both interactions and topology are strong. And if you analyze twisted bilayer graphene, if you analyze the flat bands of twisted bilayer graphene, you will find that it lives exactly in this top right quadrant, right? Now we're trying to replicate the same thing in conventional crystals. How do we even start, right? Let's now look at the concrete example, the Kagome lattice, right? This is actually named after a traditional Japanese basket weaving pattern, right? I'm showing here on the bottom left, right? At first glance, and if you remember the very beginning of the talk, you might think, well, why not just have independent atoms? Because independent atoms are by definition a flat band, but then those would be by definition topologically trivial, so uninteresting, right? So we want to build flat bands in some sort of a dynamic way from quantum interference, right? In the Kagome lattice that I'm showing here, you can write something called a compact localized state, right? And I'm showing this here in red, right? This is a linear combination of orbitals with alternating signs around the hexagon. Now here's the key. Because of the lattice geometry, any tunneling outside of this hexagon exactly cancels, right? The destructive interference is perfect. So this wave function is an exact eigenstate that I can write down for every hexagonal plaquette of this Kagome lattice, right? So if you go ahead and Fourier transform and do the proper computation, on the right-hand side, you find that you get a flat band, right, here at energy equal to 2. I'm working in arbitrary units where t is equal to 1. Right? But actually what's even more interesting is if you look at this band structure on the right, you see that the flat band actually touches the dispersive bands in one single point in the brilliance zone. This touching turns out to be protected by symmetry, and you can't gap it without either breaking the symmetries of the lattice or by making the flat band topological. And this is what I really mean by this flat bands not admitting exponentially localized symmetric 1-year orbitals. At this point, you might be asking yourself, well, okay, this is all interesting, but is it really useful for anything, right? And the answer is, of course, affirmative, right? I'm highlighting here a very recent paper, right, from last year, where they synthesized one of these Kagome metals. So even though this is a 3D material, it has many active orbitals, it has chromium atoms, cesium atoms, antimony p orbitals, you can still see here on the right-hand side a clear Kagome lattice, and if you squint at the band structure here, you can sort of see near the Fermi level, you have a flat band. Right? And the band structure as a whole seems to have signatures of the Dirac band structure, right? So we had this Dirac cone here, we also have it here, we have the flat bands. Now what's especially interesting about this compound is what happens under pressure, right? As shown here on the phase diagram on the right, the system exhibits very robust superconductivity as I apply pressure. Directly above this superconducting phase, the system is in a non-Fermi liquid state. Now, how do I know it's a non-Fermi liquid? Well, experimentalists can actually measure the resistance of a sample, right? And if the resistance, if the system is a Fermi liquid, then the resistance should vary as t squared, right? Where t is the temperature, right? So whenever you see a different exponent, and this is really what's being plotted here, you know that it's a non-Fermi liquid, right? So this is very interesting. Very likely superconductivity here does not come from phonons, right? It's actually unconventional in nature and probably akin to one in high-temperature superconductors. So this is a very beautiful example of how flat-band physics, topology, and correlations all come together in real materials, not just toy models. Okay, but this Kagome example that I gave is beautiful, is simple to understand, simple to explain, but can actually feel a little bit mysterious because I seem to have just pulled this Kagome lattice out of my pocket, right? So to really understand where flat bands can come from, let me start with a very simple example and then generalize that to the lattice case. So take a very simple planar molecule, right? 3 outer atoms shown in cyan, surrounding a central one shown in orange, all right? Now, let's say that I want to build, these are the atomic orbitals of the molecule, right? S orbitals for each atom, right? S orbitals for these triangular atoms and 1 s orbital for the central atoms. Let's say that I want to build the molecular orbitals, right? How would I do that? Well, I would use concepts from group theory, right? I can basically take these 3 atoms, these 3 orbitals from the exterior, make a C3 symmetric or a 3-fold rotation symmetric combination of them, and allow that symmetric combination to be combined with the s orbital on the central atom, right? So these will combine, right, and they will split, right? Because this is the avoided crossing rule, right? On the other hand, these orbitals here, I started with 3 orbitals. I must have 3 after I hybridize them. These hybridized orbitals here that I'm denoting with E prime, which is just notation from group theory, they really don't have the symmetry to hybridize with the central atom. So they will just stay here at 0 energy. Now, if you take this very simple picture, put it on a lattice, it turns out that this gives you the most general way of building flat bands in crystalline materials. And this is something called the Lieb lattice construction. So, in crystalline flat band materials, flat bands often appear in systems called bipartite lattices. So here's the idea. It's actually deceptively simple. Consider 2 sublattices, which I'm going to call L and L tilde. And they each contain NL and NL tilde atoms, right? Crucially, I will assume there isn't any hopping within the same sublattice. So all the hoppings, the electrons can only hop from one sublattice to the other, right? Then a 2-line mathematical proof will tell you that if you have an imbalance in the number of atoms in the 2 sublattices, you are guaranteed to get 0 modes. 0 modes which actually become flat bands once you Fourier transform. And this is exactly what we saw in this very simple picture, right? We had 3 atoms in one of our sublattice, 1 atom in the other, so we got 3 minus 1, 2 0 modes, right? It's the same game, but played on a lattice. Now, what we did in a recent paper actually was to generalize this and show some mathematical result which are very similar in spirit to topological quantum chemistry. What we essentially showed that it doesn't matter how you couple these 2 sublattices. The topological properties of the bands are only dependent on the atoms of the two sublattices, right? And actually, after our study, a different team used these same concepts on all known materials, right? And identified 7,000, that's 7 times 10 to the 3, materials, right? That have flat bands and that you can actually synthesize in a lab, right? And actually, you can even show that the Kagome model I showed previously is actually included within this formalism. And I'm showing here in this slide why that is the case. If you take the Kagome lattice and call that your big sublattice, right, and put a virtual honeycomb lattice, you can see that the same wave function for the flat band in the Kagome case is a wave function of the flat band in the bipartite crystalline lattice case. And the reasoning is very similar, right? But now, with this sort of bipartite formulation, I can get all these results without ever invoking any sort of hopping whatsoever. And this example here, I'm actually building 2 toy models of flat bands, right? So in both cases, I take my big sublattice to be made up of s orbitals on a Kagome lattice, right, these black dots, and then I vary the contents of the small sublattice. To cut a long story short, on the left-hand side, I can go ahead, use topological quantum chemistry, once again, not do a single calculation, and show that the flat band must be topologically non-trivial. And on the right-hand side, using the same algorithmic prescription, I can do the same and show that the flat band has a symmetry-protected gapless point at the gamma point, right? So it touches the dispersive band at the gamma point. And this, once again, this is not just a mathematical toy model. You can actually go ahead and apply this to real crystals, and we've actually done that. I'm highlighting here one of the compounds that shows a flat band with a band touching point that can be diagnosed with this type of prescription. Actually, if you want, you can go ahead and scan this QR code, and it points to an online database of flat bands, and in your spare time, you might want to synthesize one of those compounds. My personal recommendation is once you go to the website, you should go to this best flat bands section, because these have the cleanest flat bands. And actually, another recent experimental paper, this time from MIT, they took one of the compounds that was highlighted in this database. The compound looks something that you would never write in a chemistry exam. Is calcium nickel 2, right? And the interesting thing about this compound is that it actually has flat bands close to the Fermi level, right? So there are, here in panel A, I'm showing the result of RPES, that's angle resolved photoemission spectroscopy, right? And this essentially probes the band structure of an actual crystal, right? And you can see here that they've identified these flattish bands, right? And they've even compared them to theory. Now, if you have these flat bands quite far from the Fermi energy, then nothing really happens. But if you take the compound, you dope it. Doping means that you add different atoms with different number of electrons. You see that exactly when the flat band touches the Fermi energy, you actually get superconductivity developing, just like we did in twisted bilayer graphene. Now, I admit that 6 Kelvin, which is the critical temperature of this superconductor, is still not enough. But considering the time scale, right, on which these experiments happen, I would say that it's quite impressive. And before finishing, I just want to say that maybe discarding topologically trivial bands is not, they should not be discarded straight away. In fact, actually in a recent work, we've shown that there's a new, fundamentally different universality class of moire materials, in which the moire potential acts essentially as a magnetic field and realizes a very interesting algebra of the mirror and translation operators. Essentially, after you go through all these maths, you are able to show that these flat bands in twisted thin selenide, right, they have a very interesting quasi-one-dimensional property. So even though the system is two-dimensional, it's actually made up of one-dimensional chains. Electrons cannot hop between chains, right? But they still interact electrostatically between chains. So this actually paves the road to, for example, realizing something called the Luttinger liquid, right? And really studying like low-dimensional physics in real experiments. So with that, I'm going to leave you with conclusions and only point one more thing, the fact that because we know flat band compounds don't obey Fermi liquid theory, right? We need to come up with new tools on how to solve them. And one possible such new tool is actually going to be highlighted by the next talk. So make sure you stick for Dominic's talk. Thank you. So you're asking, you're asking outside the perturbative regime if there are any dualities between what? Between
something like ADS.
Well, I know that people are looking into that. I don't know specifically how relevant those are for real materials, but it's definitely a very interesting avenue to pursue. Yeah, but off the top of my head, I don't know of any such dualities relevant for real materials. But it's a constantly evolving field, right? So what isn't around today could very well be around tomorrow. Yeah, so the question is really about the experimental difficulties of actually realizing these platforms. Well, I must say that there are problems with growing crystalline materials that experimentalists have creatively managed to tackle. There's still a problem of actually doping the materials, because maybe you get a flat band material, but the flat band is far from the Fermi energy. You need to dope it. And people just have to be creative. They have to try a lot of things, because sometimes you just add a dopant and the dopant doesn't diffuse into the system, right? It just stays in one place, and it's actually an impurity rather than a dopant, right? So it's not really, but there aren't really recipes for that. And this is why, compared to engineered heterostructures, well, you can literally peel sheets of graphene, stack them on top of one another, put them in a dual-gated setup, and just play with the electric field to dope them. For these type of conventional crystals, there's a lot more work involved. And that's why results are probably, experimental results are probably appearing at a much slower pace. But people are working, and people are getting more and more creative. And now, probably sort of catalyzed by twisted bilayer graphene, they are understanding that this is something worthwhile, and so they're dedicating more time to it. Yes. So okay. So the question is, where do the energetics come into play? And for that, people have developed computational tools, which for the vast majority of materials are remarkably good. And I'm speaking, of course, about density functional theory, right? So it's these. I'm not a DFT person, but the way I understand it is that the programs are so powerful, you're just feeding some atom position and telling them what type of atoms you have and the distances, and they produce a band structure. Oftentimes, it can happen that the band structure is not accurate, especially if you have strong correlations. So then you actually need to get creative, right, with post-processing these DFT calculations, right? Sometimes the way you do that is, well, you rely on some experimental input, right, and you try to work out what kind of approximation can make your energetics agree with experimental measurements, right? But there are tools for finding out what the energetics are. The problem is that, oftentimes these tools are a bit like black boxes. You can't just randomly run some atomic arrangement and hope that it works. And this is where the topology insight comes into play, right? Because it tells you, okay, out of the infinite possibilities you could do, here's what is really worthwhile. Yeah. So the question is, have people thought about the mixed momentum space, real space representation or formulation of quantum mechanics, and try to apply that in the context of topological band theory? So the very honest answer to that is not to my knowledge. And quite frankly, the only interaction I had with this mixed representation was during my third year of undergrad. So there's quite some time from then. But it might be something worthwhile, especially for non-interacting band theory. It might turn out to be insightful. So maybe people will look at that. Yeah. But to my knowledge, I'm not aware of anything. Well, actually, okay, so that's a very interesting observation. And it's related to something that we've done recently. It turns out that some of these topological flat bands, right, you can't really trivialize them, but you can do a basis transformation and actually convert them into a heavy fermion model. So there is a duality between some of these flat bands and heavy fermions. As a matter of fact, twisted bilayer graphene, you can do an honest-to-God unitary transformation on the band structure and map that to a topological heavy fermion. So then you can actually use a lot of the techniques from there. For this specific experiment, right, obviously there are no F electrons in this compound, so it's not a heavy fermion. But it could very well be that you can take some of these, you can take some of the momentum states, right, do some band inversions, and construct F-like electron state for the flat band, and then re-express the same sort of physics in the language of heavy fermions. But that's definitely something possible, and people have looked into that into great detail. Thank you.
Okay, I think we have to move on, so let's thank Dumitru again.